So this is, I think all the periods we got through number 1, right? Number 1 on worksheet 2 is just finding critical numbers. The additional complexity with number 1 is just having to work that denominator into a fraction so that we can find critical points appropriately. So any questions with number 1? Okay. I started going through number 2 with 7th period, and so this is what we've accomplished so far. I can continue with this problem. It says find the absolute extrema. We know we're dealing with extreme value theorem, so we can state EVT. And the fact that we're dealing with a polynomial, so there's no breaks in the graph, no vertical asymptotes, so we can state our conditions. We know our function is continuous. On the closed interval from -3 to 1. And now our next task is to try to find some critical points. Right? We know endpoints are candidates, but we want to seek out some other candidates, and they're going to come from f prime. So from f of x, we go through power rule, we find the derivative, set equal to 0. Solve for x, we get 0 and -4. Okay. So what decision do we have to make after we find our critical points? Okay. How do we know whether to keep them or not?
They're between
Good. Between the intervals, right? We only want to keep what's between the intervals. So we see that -4 is slightly outside the interval. 0 is inside it. So we'll keep 0. We'll remove -4. So it leaves us with 3 critical points to test, right? We have 2 endpoints and 1 critical point, and they all go into the original function. And then we can then determine the absolute max and absolute min. Okay. So -3 in for x. -27. Okay. Remember that as we are testing our critical points and endpoints, they go back into the original function, right? We don't want to test these against f prime. That's not going to give us what we want. We want the locations of the highest and lowest points. So our decision is based purely on our y values. Highest is our absolute max, lowest is our absolute min. 0. All right, any questions so far?
So I know it's just algebra, but can you explain how you got the 4 to the power of 2 over 3?
Right, this one here.
Yeah, on the last one.
So I want the x to be by itself. Oh, you're talking about from here to here, from here to here?
Yeah.
Okay, so I just decided to square the 4 and leave the 3 as a cube root. So 4 squared is 16, and then 16 to the 1/3 is the same thing as cube root of 16. So 4 to the 2/3 is same thing as 4 squared to the 1/3. I can kind of rearrange my number however way I want to.
Yeah.
And then I can make this 16 to the 1/3. And that's the same thing as cube root of 16. But you can leave it like 4 to the 2/3. That's fine. It's just I'm just showing some different variations. That's all.
Okay.
All right, everybody good with 1 and 2? Number 3, we want to apply Rolle's theorem. So Rolle's theorem is kind of like mean value theorem, but it's a little bit more restrictive because we want to guarantee a slope, but the slope that we want to guarantee has to be 0. We need and we want a 0 slope. So our initial conditions are going to feel similar with mean value theorem. We're still going to write our conditions of continuity and differentiability, but now we have an added step. Is that we need the endpoints to be at a very specific location. We need the endpoints to be directly across from each other. Because the only way that we can guarantee a slope of 0 is if our endpoints are directly across from each other. If I can draw a horizontal line between my 2 endpoints, then that's going to ensure that my graph is going to hit a slope 0 somewhere between. Right, so I have to ensure that this is true first. But first two conditions, continuity. Sorry. Now I need to find f of 2. I need to find f of 6. Okay, so tell me what you get when you plug in 2 and 6.
-7.
Okay. So -7 and -7.
Why are you plugging 2 and 6 in?
Because it's very similar to mean value theorem. We want to ensure that our endpoints have a specific slope that we're after. So if you think about mean value theorem, which is essentially Rolle's theorem, before we can set the derivative equal to a number, we have to figure out what slope that we're after. So if my endpoints can produce a specific slope, then that is the slope that we want to guarantee.
Okay.
But because these are the same value, what's going to happen when I find slope between these four numbers here?
0.
0. So it's basically mean value theorem, but Rolle's theorem says I need to have slope 0. So to ensure slope 0, we just need these two y values to match. If they're matching, we know it's going to work out where I'm always going to be able to set my derivative equal to 0. Okay, any questions with mean value, with the steps that we need for Rolle's theorem? So this is the third condition. Third condition is asking for us to compare f of 2 and f of 6. Are they equal? If they are, the slope between the endpoints will always give us 0.
Mr. Yang?
Yes.
If your slope for this part 3 doesn't equal 0, would that be the end of the problem?
Exactly. Yep. If this didn't equal to 0, then we can't guarantee slope 0. So Rolle's theorem would not apply, but it will still be a perfectly fine mean value theorem problem, right? It could be a slope of 1/2, could be slope of 3. So, but that's not good enough, right? This is specifically asking for Rolle's theorem. So yes, the problem would end if I cannot guarantee a slope 0.
Okay, thank you.
But it would continue if it was 0 or any other number if it was mean value theorem. Okay, so I put MVT here just to show you that Rolle's theorem is basically mean value theorem. It's just that we need these two values to be the same. Okay, so then our next step, Rolle's theorem, is we're always going to set f prime equal to 0. That's Rolle's. So we have 0, right? We have the 0 insured on the right side. Now we have to find f prime. So f prime, we go through power rule. We set f prime equal to 0. Solve for x. And that is also our c value. So this is telling us that at 4, the graph is going to achieve a slope of 0. And 4 is somewhere between 2 and 6. So we can guarantee that there's a location between 2 and 6 where the graph is going to hit a slope 0. All right, any questions with the Rolle's theorem? All right, mean value theorem. So mean value theorem, polynomial. So we know our conditions will not be an issue, but we do have to take the time to spell them out. So now we have to work our formula here. Okay, so where would you start?
Plug in 1, 2.
Good. Plug 1 and 2 into the function, right?
Yeah.
Let's figure out what slope can we guarantee, and then we can use the derivative to find the location of that slope. All right, we have our endpoints. What's next?
Do we plug it into the MVT function?
Yeah. Let's find out the slope, right? Let's figure out what slope we're targeting. So it's change in y over change in x. Okay, so this portion looks good. We have this piece replaced with a number. What's next?
Do we have to find f prime of x?
Yep, so now we can focus our attention on f prime, right? F prime is going to help us find the location where this particular slope is going to live on the graph. So we have the pieces that we need. We have our slope formula, we have the slope, and now we can use this to figure out the location of a particular slope. Okay, set them equal. Solve for x. Take the square roots, plus or minus. So it looks like we have two locations on the curve where there's a slope of 6. So can we keep both of them?
No, one's outside of the values.
Good.
We have to check in the interval.
Good, good, good. Yeah. Our problem is only concerned about 1 to 2. So yes, there may be another solution, but if it's outside the interval, then it's not part of our problem, right? So it looks like the negative is out.
So Rolle's theorem is only applicable when f of a and f of b are equal.
Yeah.
They have the same value.
Same y value.
Mhm.
Yeah.
And then from there, what do you do? Like, what's the further step after you can find that Rolle's theorem is applicable?
Then, because your endpoints are the same, your slope is going to be 0. So
Yeah.
it's the same thing as mean value theorem. It's just that mean value theorem, we're setting f prime equal to whatever slope we find. But Rolle's theorem is setting the derivative equal to slope 0 because it's like a guaranteed slope 0.
Well, isn't it like the same?
It is the same. Exactly. Yeah.
It's just called Rolle's theorem because you get 0.
Exactly.
Okay,
Yeah.
You don't do anything differently in the. Okay.
No. Yeah. So think of Rolle's theorem as just one specific scenario of mean value
You
theorem.
get 0. Okay.
Right. But because we're looking, a lot of times we're looking for slope 0 so many times, we have a specific name for that particular situation. Yeah. Good. All right. Any questions with the first page? All right. For those of you on Teams, are you guys okay?
Good, thank you.
Good. All right. All right, let's go to the back, number 5. My paper didn't show up very well here. So my function here is x squared over x squared minus 9. So this problem says find relative max, relative min, increase, decrease. So this is the first derivative test. But let's point something out here because this may be helpful down the road. Is this a polynomial?
No.
Not a polynomial, right? Is there anything that stand out about this problem that will give us a picture as to what's going on?
There's a vertical asymptote.
Okay, there's a vertical asymptote. Okay, how would you find that?
Set the denominator equal to
Okay,
0.
denominator equal to 0. So if I ever see a denominator, I think it's helpful because if you know that there's a vertical asymptote, you're going to end up putting them onto the sign line, but it's nice to know that if there's an asymptote, we're not going to be confused by the signs around it, right? We're not going to be thinking, oh wait, it's a decrease followed by increase, so there must be a relative max. If we know that there is a vertical asymptote, we know that it doesn't matter what's happening around it, that point can never be a max or min. Okay, but yes, but there's a vertical, in fact, there's more than one here. If I solve for x, I get x squared is equal to 9. Take the square root of both sides, I get x is equal to 3 and x equals negative 3. Okay, so these numbers will show up later, but it's just nice to know just some information about a graph, right? Okay, so first derivative test, everything is going to come from f prime, so let's go ahead and find f prime. What rule is required here?
Quotient.
Quotient rule, okay. Okay, clean up your derivative. So careful, right? We don't cancel anything out. We have to distribute the numerator out. All right, so I have my f prime. What's next?
Find critical points.
Look for critical points. And where do we look for critical points?
The derivative.
Okay.
Vertical asymptote.
Okay, so numerator and denominator, right?
Yeah.
Okay, good. So we have to set the numerator equal to 0, the denominator equal to 0. So the numerator gives us,
But you don't use vertical asymptote for critical points.
we do use them for critical points. We're going to place those asymptotes on our sign line. And some of you may be thinking, well, why do we put the asymptotes on the sign line if there's no chance of it being a max or min? Anybody have any thoughts? Why do we want to place these onto our slope sign line if these have no chance of being a max or min? Are max and mins the only purpose of the first derivative test? What else can we gather from creating a slope sine line.
What intervals the function increasing?
Right, increase and decrease intervals. So the asymptote will be on the sine line, not because it's there to help us find max and mins. It's going to be on the sine line to help us create some boundaries for our increase and decrease intervals. Okay. Good. So we have x equals 0. If you set the denominator equal to 0, you'll get plus or minus 3. So here is our slope sine line. Okay. Choose values in each interval. So I'll choose -4, I'll choose -1, I'll choose 1, I'll choose 4. Okay. And how do we test those points?
Something to the, oh, that you plug them into the, not the derivative, but the original equation.
Well, maybe eventually, but right now we want to, the reason why we want to test -4, -1, 1, and 4 is because we want to know what the behavior of the slope is. So if we want behavior of the slope, that's going to come from the derivative. Yeah, good. So our test points are going to go into the derivative. Now, this seems like a lot of work to plug in, right? But we have something to kind of help speed up the process. What do you notice about the denominator? That's going to make it easy. Because we only care about the sign, right?
Would the denominator have to be positive?
Yeah, see, the denominator is always positive. So really, we can ignore the denominator for this entire process. It's always positive. So we just have to worry about the numerator. Whatever the sign is for the numerator, we know that's going to be the sign of our derivative. So let's plug -4 in for x. -18 times -4. That's a positive number. Positive over positive is positive. So our graph is rising. Okay. -1 in for x. 2 negatives gives me positive. Okay. Plug 1 in.
Negative.
-18 times 1 is negative. Okay. Plug 4 in.
Negative.
So we have one relative max, right? Which is at 0. No relative min. We have intervals of increase and decrease. Okay, so how would you write your interval of increase? Good. Right, we need to separate our statement. Yeah. There's a relative max at 0 because f prime changes from positive to negative. And I'm looking for these because statements. Okay, how we're doing there?
I have a question for critical values.
Okay.
So you set both the numerator and denominator to 0.
Yeah.
And you use the vertical asymptote.
Mm-hmm.
Do you set the original equation's denominator and numerator to 0 as well?
For
Critical points.
Oh, you mean f of x?
Mm-hmm.
There's going to be some overlap, but I would say from the original function, if you see a denominator, just go ahead and set the equal to 0, just so you can have some visual perspective, so you know that you're dealing with an asymptote, so that when you get to the sign line, you won't get thrown off if you see a positive and negative.
Okay.
Right? If you see a positive and negative, if you didn't know that was a vertical asymptote, then you may be tempted to say that's a relative max, relative min.
Mhm.
But if we can just put that off to the side from the original function, it'll give us some perspective, so we don't get confused if we see signs that are misleading us.
So if the f of x was x squared minus 9, just that, you wouldn't set that to 0.
Oh, with no denominator?
Yeah, with no
Yeah,
denominator.
I wouldn't set it
Okay,
with
so
0.
you're
Right?
only doing it because of the denominator.
Because it's a denominator, right?
Right.
Because I just want to have some perspective for my slope sign line. Yeah.
Okay.
Yeah. But if you were to set the original function equal to 0, if there's no denominator, then what you're finding is you're finding x-intercepts, which is nice for graphing purposes, but it doesn't help us in our problem. Yeah. Okay, good. Any other questions with 5? Okay, number 6. We're finding intervals of concave up, concave down, point of inflection. It's going to feel like a similar process, but number 5 is just all the work that we're starting from is with the second derivative function. Okay, so here's number 6. We're going to work our way down to f double prime. I'm sorry, I got to do f prime first. All right, second derivative. Okay. All right, now we can set this equal to 0, right? Find our critical points. Okay, what can we do now?
Plug in critical points.
Yeah, let's create our second derivative sign line, right?
Oh, yeah, sorry.
Yeah. Choose numbers around. And where do we evaluate these numbers?
So prime.
Good. I like the factor form because it gets me to the sign a lot faster. So 6 times -1 times a +1. So only one negative. So, okay, now with the second derivative, our symbol that we're going to draw is going to be a concave down, right? This negative doesn't mean negative slope. It means the curvature is concave down. Okay, plug 1 in. Positive times positive. Plug 3 in. Positive times positive. -1. I messed up. Sorry, guys. -2 and 0. I got my numbers mixed up. So everything is off here. Okay, -2 and 0. So I have a different set of numbers I need to choose. So -3, -1, and 1. All right, this is better here. 6 times -3 is negative, times -1 is negative, so 2 negatives gives me positive. There we go. Okay, concave up, plug -1 in. Negative times positive is negative. +1. Positive times positive is positive. Okay, we are ready to make our statements about intervals of concave up, intervals of concave down. Okay. How many points of inflections do you guys see? 2, right? Because there's a change in sign in both. And when you're ready to make your statements, these test points are no longer used. We're just relying on -2, 0, and negative and positive infinity. Okay, so here are the statements. Okay, number 7. All right, see you, Alex. 2. Number 7 says, use the second derivative test to find relative max and relative min. So first thing is we're going to find f prime. And then we'll test those critical points with the second derivative function. Right. I want to factor this. I like to factor with my first term being positive. So I'm going to take out a -1. Solve for x. We get 5/3 and 3. So these are the potential answers that we have. So now to test these candidates, we're not going to use a slope sine line. We're going to rely on the second derivative function. Hence the name second derivative test. Okay, plug the critical points in. All right, I got 24, but how do we interpret this number here? Is the value that important?
Since it's positive, does that mean it's concaving up?
That's right. Yep. Concave up. So it helps if we draw a picture of it, right? If we're dealing with a concave up graph, then this must be a relative what?
Min.
Min, yeah. All right, don't involve the 24 as your ordered pair, right? This 24 is not from the original function. So that 24 is just telling us it's concave up. It's not going to have any other relevance for our problem. So I see some students, they want to include this as the ordered pair, but that's not the y value. Okay. Evaluate the second derivative at 3. I get a -4. The value is not that important. It's the fact that it's negative. So negative value from the second derivative means concave down. If you picture what concave down looks like, and then the only place on this graph with the slope 0 is here, and that is obviously a relative max. Hey, any questions here? Okay, let's see if we can sketch a graph based off of this information here. The easy part is plotting all these ordered pairs. These are there to kind of help provide us some anchor points for our graph. Okay, 0, 4, 6, 0, 2, 0, and 4, 2. These next statements are all about f prime. So let's see if we can organize this information onto a slope sine line. So if you read these statements here, can you tell what critical points, where the critical points are? What do you guys think? What x value highlighted in those statements?
Would it be 0, 2, and 4?
Is 0 representing an x value?
No, actually.
Yeah, this is
so it would
talking
be
about
0.
slope, right? So what are the only x values that we see represented in these statements? Okay. What about 2 and 4? Right, everything is relative to 2 and 4 here. We see 2, we see 4. These are all referencing x values, right? So let's place them onto our sign line. They will kind of help organize our information a bit. So the next decision is whether we're going to be making some of these intervals positive or negative. Let's read the first statement. F prime of x is less than 0 for x is less than 2 or x is greater than 4. Can you guys rephrase this in a different way that's more visual? What's another way of saying f prime of x is less than 0?
The slope is less than 0?
Okay. Okay, so in other words, slope is what? Slope is
Negative.
negative. Okay, slope is negative, right? So where is slope going to be negative?
When x is less than 2 or greater than 4.
Yep. To the left of 2 and to the right of 4. Negative slope. All right. Are any of us having trouble converting this statement into a diagram? Okay.
I just find that I sometimes get kind of confused when I do it by myself. I know, like, it makes more sense now, but I just find sometimes I mess up the steps kind of when I'm doing it by myself.
Yeah, I think it's hard to look at this and try to get to the graph. I like to go through this process first. Gives me something more concrete to put onto my graph. Yeah. What does this next statement say?
Is it saying that there's like a vertical asymptote there?
I think that's possible. All right, it doesn't specify that what type of issue it's having, but it could be a sharp turn, it could be an asymptote. Either way, slope doesn't exist. Okay, so there's a couple of different ways that we can show a slope not existing. One way is having a sharp turn, but you could also do vertical asymptote as well. Okay, what does this next statement say? Or what does this mean? F prime of 4 is equal to 0.
Would that mean that the x value of 4, the slope is 0?
Yeah, slope is 0 at 4. And then what about this next to last statement here? F prime of x is greater than 0, where 2 is less than x is less than 4.
So between 2 and 4, the slope is positive?
Yeah. Good. All right, second derivative. We have one statement. Second derivative is less than 0 for x does not equal to 2. What's another way of saying this? Okay. Second derivative is less than 0. Can you say this a different way? concave what?
Would it be down?
Concave down. Where's the graph concave down?
Everywhere except for 2.
Everywhere except for 2. And so that 2 is also going to go onto our sine line. But now we're going to force everything to be concave down. So my suggestion is let's create our big picture graph. And then we can go in and then fine tune our curvature a little bit later. We know our graph is going to follow this path, right? It's going to be decreasing until it hits 2, increasing until it hits 4, and then decreasing until it keeps going. We know there's a slope of 0 at 4. We know we can make it a sharp turn at 2. So initially, this is maybe what I was thinking. I'm not even worried about the slope right now. Okay. At least I know my graph is even without knowing second derivative, I know that that's true, right? My graph is going to be decreasing, then increasing, then decreasing. Okay. It's not my final product, but it kind of gives me some idea, right? I have a general idea, and the second derivative is going to go in and try to make it more fine-tuned and more a better match in terms of its curvature. But are we okay with the first derivative just creating something that has that slope behavior? Okay. All right, we're going to add this second derivative feature into our graph. We know that we want this to be a sharp turn. We want this to be a slope 0. Okay, so here is my updated graph, but this is going to help me out. Okay, so I know up until 2, I want my graph to be concave down. So I want that concave down shape, but it's going to have to follow this path, right? It's never going to come down. It's always going to be decreasing. So, right, that's a better fit for the curvature that we're trying to achieve. Concave down, but maintaining a decreasing slope all the way through. Okay. Sharp turn, what's going to happen the rest of the way? Concave, still concave what?
Down?
Yeah, still concave down, but it's going to have to follow the rest of this path. But I can make it a matching curvature with what I want, right? So sharp turn still, slope 0, and looks like my graph is going to fit nicely there. Okay, any questions there? Okay. You guys have any final questions from this worksheet? All right. So tomorrow afternoon, well, tomorrow in class, I'm going to go over worksheet 3. And whatever I don't finish, I can cover in tomorrow afternoon session from 4 to 5. Okay. But yeah, hopefully you guys are feeling more comfortable with this material. I know this can be a little messy, but if we can break it into smaller steps, gather information about slope, sketch some version of the graph, and then we can go back and fill in a better picture of the curvature of the graph. All right, thanks for being here, guys. I will see you tomorrow.
Thank you.
All right,
Thank you,
take care,
Mr.
guys.
Schmidt. Have a nice day.
Yeah, you too. Bye.